so pretty much everything we talk about today to do with graphs should be familiar, okay? Because you went over position versus time graphs, and you went over velocity versus time graphs in Science 10, okay? They still graph the same thing as they did last year when you learned about them. So we're just going to review those graphs in particular, as well as a few kind of fundamental things about graphing itself, okay? Like quick review, y equals mx plus b, and that kind of stuff, okay? And then we'll be kind of moving forward there towards doing a lab, okay, you know, having some stuff that's running that we're recording and getting some stuff done in that. Okay, so hopefully this stuff should seem familiar to you. All right, so we need to understand what kind of information can be read from these two types of kinematics graphs, and understand that graphs and equations show the same information in different ways. So that is the stuff that's on your formula sheet. Most of that is derived from some sort of graph. Okay. All right. So with a position versus time graph, what a position versus time graph tells us is where the object is at various points in time. Okay. And that's important because it allows us to calculate other things about that object, mainly its velocity. We could also use it to calculate its acceleration if we really wanted to. Right? We can also calculate things like total displacement, total distance traveled, and things of that nature from a position versus time graph, because all we need to know is where the object is and what time it is. Okay. So if I am looking at this graph here, right, in this first part of the graph before this circle, right, so this is just a straight line. Okay? It's just a straight diagonal line. What is the object doing during that section of the graph? So if I have a position versus time graph where the line is going up by the same amount every single time, what is the object doing? Traveling at a constant velocity. All right? We know it's a constant velocity because its position changes by the same amount every time interval. That's why it's a diagonal line. It's constant rate of change. Everybody follow me on that logic there? Okay. If it's a constant diagonal line, okay, then the amount the position changes is the same every second or hour or minute or whatever the units of time are on that position versus time graph. All right, the next section of this position versus time graph is showing a line that is curving. Okay, and that curve is getting flatter and flatter as it goes along. Now, it says right beside that section that during that section the object is decelerating, which is not a term we use in physics. Okay? In physics, any change in velocity is an acceleration. Acceleration can be positive or negative. In this case, this would be a negative acceleration because the velocity is decreasing. Okay? Everyone all right with that? So when we see an object whose velocity is changing, right, that means that the amount of distance it covers every time interval is different because its speed is changing. So here, where it was going very fast, the line is steeper. But as we get closer and closer to this part, it's getting flatter and flatter and flatter. What is an object doing when its line is perfectly flat? What's not changing when its line is flat on a position time graph? Okay, yep, that's not changing either, but one other thing is not moving. Its position isn't changing. It says right here that for this time interval here, so from 0.3 to 0.5, okay, it doesn't move. Its position stays at 0 for that length of time. Its position doesn't change, so it's a horizontal line. Okay? And in this part of the graph, in the blue part here, what we see is a gradual change in the rate of change of position as we get to there. So the line gets flatter and flatter and flatter because we're going slower and slower. And the slower we go, the less we change our position every time interval. So the line approaches flat. Everyone follow me on that? Okay, then this other part here would be the exact opposite of that. Right? So after 0.5 seconds, right, we see that the line curves upwards, which means that in this time interval here, I changed my position by this much. But in this time interval, my position changed by more, right? I went farther between 0.6 and 0.7 than I did between 0.5 and 0.6. The only way for me to go farther in that time interval is if I'm going faster. Right? So in this case, the acceleration is positive because the object is going faster and faster. And the same would be true here. If I go over to 0.8, okay, this is a bigger change of position than this one was. Okay, we're going faster and faster. Now, as we get to here, okay, this part is just diagonal again. So we're traveling then at a constant rate because our position is changing by the same amount every time interval. Right? These are the things we have to be able to read off of a graph. If I throw a graph in front of you, one of the things I'd expect you to be able to do is exactly what we just did here. I would label these sections, maybe like and my expectation would be that if I asked you what is going on in section B, you'd be able to say the object's velocity is decreasing. Okay? Or the object is slowing to a stop, or something that describes what's going on in section B. Right? If I asked you what's going on in section E, you would tell me the object is traveling at a constant velocity in a positive direction, or forwards, or something like that. Okay? Because if you say velocity, then you have to give me a velocity is what kind of quantity? Vector, so you'd have to give me a vector on that. All right, so that's an expectation kind of right off the bat in Physics 20 is that you can interpret what's going on by looking at a graph. Okay? There's also going to be some expectations for things you can calculate, but interpretation is the most important skill you can have. I should be able to throw any graph in front of you, okay, as a grade 11 student, and you can interpret what's going on in that graph. All right. Now, slope calculations, okay? Some people, okay, and some math teachers like to teach you this whole slope equals, okay, y2 minus y1 over x2 minus x1 thing. And while that always calculates slope, that's all it does. Okay? It doesn't help me to extrapolate beyond the graph or calculate points on the graph or things like that. Okay? So its use is limited, which is why we use this. Okay? How many people have seen the graphing equation before? Good. I should see everybody's hand up. Okay. Y equals mx plus b. What does y stand for?
The y-axis?
Okay, or the y value, yeah, of any point on the y on the graph. Okay, so sorry, I'm just going to get rid of this thing here. Okay, so if I was looking at, let's say, this point right here, right, y would be whatever this number is. Okay, x similarly would be whatever this number is. Okay, it would be the y and x coordinates essentially of a given point on the graph. Okay, what does m stand for? The slope of the line. Okay, what does b stand for? The y-intercept. Okay, and the y-intercept would be where this line crosses the y-axis, which this one doesn't, so I'll have to make it do that. Okay, so this would be b right here. Okay, we're going to use y equals mx plus b quite a bit in this unit. Okay, especially when we do our little graphing lab, because we'll be asked to do things with a position versus time graph, like calculate how far the object would have gone in this time interval that is beyond what we measured. So if we run an experiment that only runs for 40 seconds, y equals mx plus b can help us to calculate how far, and y on this graph is, okay, position, how far it goes in 2 minutes. We didn't run the experiment that long, but the graph can tell us that. Okay? We can use y equals mx plus b to extrapolate, that is, go beyond the graph. Right? Or it could ask you, given your graph, how long would it have taken to go 100 meters? When in our experiment, things only went 35 meters. Okay? We can extrapolate beyond the data we have with this formula. Okay. All right. On this particular graph, which is a position versus time graph, we've said that y represents the position of the object. Okay. X represents the time. So what does B represent on this graph? Mason?
The starting.
Right. It's the initial position of the object. This is where the object was at time 0. Okay. Again, these are things we have to be able to interpret from a graph. At time 0, okay, where the line is, B, is where the object was at time 0. Okay. If I'm looking at this formula here, and I want to calculate the slope, obviously I have to manipulate for m. So I would subtract B and then divide by x. Okay, and that would give us the slope of the line. Now, Mason just told me that B is the initial position of the object. So in this case, if I'm looking at this as being my other point, what's this y value? If B is the initial position, this would be the final position. So really, this formula is going final position minus initial position. And what does x represent? Time. What does this formula calculate? What's final position minus initial position? Okay, okay, this formula as a whole, yes, calculates velocity. What is final position minus initial position? Displacement. So really, this line and the slope of it represent the velocity of the object. Okay? In Science 10, you may have just memorized stuff like that. Right? You might have just memorized, okay, if I have a position time graph, the slope is the velocity, and then, on a velocity versus time graph, the slope's acceleration, the area under the line is this, and blah, blah, blah. You might have just memorized all that, which was probably fine in Science 10. You only had 2 graphs. Okay? By the time you're done Physics 20, we'll have gone over probably close to a dozen different kinds of graphs. And when you're done Physics 30, it could be 30 or more. Are you going to be able to memorize what you get from all 30 different graphs? Probably not. That's a lot of memorizing. Okay? What's a more important skill is what we just did. I analyze the graph and I figure out what the slope represents instead. Then I don't have to memorize it. Okay? I can figure out what the slope of any graph represents by doing what we just did. Okay? I manipulate it for slope and I figure out what did y represent, what did b represent, what did x represent. Now I have a formula. Now I know what the slope represents. I can do that on any graph, and then I don't have to memorize the slope of 30 different graphs. Okay? Everybody with me there? All right. So, case in point here. I give you this graph and I ask a few things. Maybe one of the things I ask is, what is happening in part A of the graph? Dominic, what's happening in part A of the graph? The object is moving at a constant velocity. Positive or negative? Positive, okay? Again, if we say velocity, we need to indicate either forward or backward or positive or negative. Okay? All right, what's going on in part B of the graph? Marion, what's going on in part B? What's happening to the object's position here? Not changing. Okay, so the object is standing still. Okay, not going anywhere for part B. Okay, what's going on in part C? Right, it's now moving at a constant velocity in a negative direction, right? Because its position is becoming more and more negative, but it's doing so at a constant rate. Okay? Is there any point on this graph where the object is accelerating? Are there any curves on this graph? Right? There's no curves anywhere on this graph. So there's no place where the velocity is changing, okay, over a section. Right? There's constant velocity forwards, no velocity at all. Constant velocity backwards, no velocity at all. Okay? And in E and in F, are those both constant velocity? Which one is the object going faster, E or F? E. How do I know E is faster? Yeah, it's a steeper incline. The slope is greater, right? The object is changing its position more quickly in E than it is in F. And I could analyze that mathematically if I needed to. Okay, this only takes 1 second. Okay, this is 1 second here. And it changes its position from -10 to -4 in 1 second. And then it takes 4 seconds to go from -4 to 0. It's definitely going slower there. Okay, I want you guys to calculate for me the total displacement of this object over the 17, let's say it takes 18 seconds. Let's say it goes all the way to 18, so this part here is flat. Okay, what's the total displacement of this object over the entire trip? 0. Initial position, 0. Final position, 0. Okay, we started and ended at the same place. So then what's the average velocity over the whole trip? 0. Remember, velocity is displacement over time. The total displacement was 0. The velocity's got to be 0 as well. Okay, that was the stuff we worked on last week, V equals D over T stuff. Okay, this one will take a little longer. Total distance traveled. You'll probably need to write a couple of numbers down to do this one, just as a hint. Yes. Yes, you do. $32 meters. I think that's about right. Okay, here's how we arrive at that. Okay, total distance traveled is how far did the object go. Doesn't care which way it went, just how far did it go. All right, so in section A, we change our position from 0 to 6. That means we went 6 meters. Okay, how far did we go in B? 0, we didn't go anywhere. Okay, in part C, we go from +6 to -10. So that's 16 meters. Again, this is distance. It doesn't care whether I went forward or backward. And then we go from -10 back to 0, okay, over the next 2 sections. Okay, so that's another 10 meters. All right, so 26 plus 6, 32 meters. What's the average speed over the whole trip? Probably need a calculator for that one. Does that formula calculate speed? Speed is distance over time, right? All right. So we just calculated the total distance. It's 32. How long does the whole trip take? 18 seconds. 32 over 18, but 1.8 something? 1.78? Okay, done. These are exactly the kinds of things I would ask you on a quiz or a test to do with graphs. Okay? Like a graph like this, I could ask probably 8 different questions from. Right? Like here's another one. I want to know the average velocity between 0 and 6 seconds. Okay? Is that how I calculate velocity? Right? I can't use slope here because there's no line that directly connects 0 and 6 seconds on this graph, is there? Right? So I can't use y equals mx plus b. That's not going to work. Okay? So I'm going to go total displacement. I go from 0 to 6 meters, and that takes 6 seconds. Looks like my average velocity is positive 1 meters per second. Okay, we're going to have to shake off a lot of this summer rust, I think. Okay, these are questions that should happen pretty quickly for us because they just involve us reading a number and plugging into a simple formula on the graph. Okay, there's really nothing overly complex, mathematically speaking, about a position versus time graph. The only things you're ever going to be asked to calculate from this are displacement, distance, speed, and velocity. Okay, and all you're going to use are v equals d over t, v equals d over t, and final position minus initial position. Okay, if it's a single line graph, then you do use y equals mx plus b. Okay, but you'd use that for any single line graph. All right, questions on what we did there with that graph? Okay. Now, we were talking about trips that had 2 parts the other day. Okay, and we were talking about why, if I want to calculate the average velocity, that I have to use the total displacement divided by the total time. I couldn't just add the velocities all together and divide by the number of sections. Okay, and this graph here is illustrating kind of why. Okay, on this graph, in the first section, we go 50 kilometers per hour. That takes 2/3 of the whole trip. Okay, in the last third of the trip, we go a lot faster, twice as fast, in fact. Right, but my average velocity isn't 75. It's 67 because I did this for more of the trip than I did this for. Okay, so we always have to weight it, okay, accordingly. That's why we use total displacement over total time and why we don't just add the velocities for each section together and divide by the number of sections. Okay, we have to weight it, okay, so that it reflects how much of the trip was represented of each part. Okay. Now, once in a while, not very often, but once in a while, a question will ask you to calculate the instantaneous velocity of an object. Okay? If it's asking you to calculate the instantaneous velocity of an object, then that means more than likely that the object is changing its velocity. In other words, it's accelerating, which is all that is going on this graph. Okay? Everywhere on this graph is all curves. Right? So the objects in part A, is the object speeding up or slowing down? Yeah, it's speeding up, right? The line's getting steeper and steeper and steeper, okay? And then in part B, okay, we've got like kind of this hump, and then in part C, we can see that it speeds up, but then at the very end here, the line starts to flatten, which means it's actually slowing down, yeah. Okay, at the very end here, it's slowing down. For this part, it would be speeding up, but for this part here, okay, it's slowing down. So you got a getting steeper, and then you got a getting shallower part. All right, if I want to calculate exactly how fast the object is going right here, okay, I can't use v equals d over t, because v equals d over t assumes that v is not doing what? Yeah, not changing, right? It's assuming the speed is constant. So I can't really use that, right? I know the speed is changing, so I can't use that. So what I have to do is I have to use the only thing I understood in university calculus, okay? I did not understand anything but this one thing in university calculus, okay? I passed university calculus, but only because I memorized all the examples in the textbook and wrote them down on the final exam and got part marks for method. I don't recommend that as a way to be successful in university calculus, but I only had to take one calculus course and it worked. So, okay, here's the one thing I understood, and it was the first day. Okay, to a mathematician, a curve is an infinitely large number of infinitely small straight lines that are all strung together. Okay? Something like if you were looking at like a low resolution picture or video online, you can see the pixels, right? The little squares, right? That's how your computer makes images, right? It uses all these little squares. The higher the resolution, the smaller the squares are, to the point where we can't even see the squares anymore, right? But if it's low resolution, you can actually see all the little squares. So essentially, this line is made up of a whole bunch of little straight edges, but they're so small that I can't see them. So what I need to do is I need to make the little tiny straight line that exists right here long enough that I can calculate its slope. Okay? So what I have to do is I have to draw a line that is tangent to the curve at that point, because a tangent line will be parallel to the curve at that point. In other words, parallel and having the same slope as that imaginary little tiny line that exists there. Okay? So they've kind of done that with this triangle, but it's not long enough, so I'm going to make it longer. Okay, so something like that. Okay, now I have a line that's long enough that I can get a couple of points on it and use, like y2 minus y1 over x2 minus x1, or y equals mx plus b. If it went far enough down that I'd know where b was, I'd be able to calculate its slope. Okay, or I'd be able to go total distance over total time. Okay, I'd be able to do that. Okay, so let's just say I'm going to do that method. I'm going to pretend that it went through this intersection here and this intersection right here. Okay. So I know the rise of this line is from 2 to 8. So the rise is 6. Okay, and the run is from 6 to 14. It's also 6. All right, so my average velocity, or sorry, my instantaneous velocity at point A is 1 meter per second. If I did that up here, the line would be a lot steeper, which makes sense. The object is accelerating. My instantaneous velocity further up there should be faster. Everyone follow me so far? Okay, it's very rare that I will ever ask you to do that, but you need to know how. Okay, the reason it's very rare is if I ask you to do that, everybody draws their own tangent line. How many different answers am I going to have? Like a lot, right? No two people are going to draw that line exactly the same. So I have to have this like range of answers that I would accept, which is a pain in the neck. So I probably won't do it, right? But as long as you know how. All right. What's the instantaneous velocity here at point B? Okay. We said we have to draw a line that's tangent to the curve, right? All right, so let's do that. Let's draw a line that's tangent to this curve. What's the slope of that line? 0. Yeah, it's horizontal, right? So what's my instantaneous velocity right there at the top of B? 0, right? How many people are getting a picture in their mind of what this motion looks like in real life? Okay, that could be one. Okay, it could be one, or it could be this. Okay, this part right here, where the object is accelerating, is me pushing the brush upwards with my hand. I'm accelerating it upwards. As soon as it leaves my hand, what's it start to do? It starts to slow down because gravity is pulling it back down. So gravity is right here. Gravity starts to pull it down, down, slow it down, slow it down. At the height of its flight, it stops for just an instant, and then it starts to fall back down at exactly the same rate. Notice that the two sides of this thing are exactly the same. Okay, so the rate of acceleration on both sides of this curve are the same. And then right here would be the start of me catching it and slowing it to a stop. Okay? That's the next step. That's the thing we didn't ask you to do in Science 10. The next step is be able to look at a graph and envision what's actually happening. Then you'll live in my world, which is weird and different, but you'll get the hang of it. All right, so we just did that. We don't need that one. Okay. So let's say we have this one. Okay, so this question here with this graph. Okay, so we have a bus that makes this trip according to this position time graph. The average velocity, I want to calculate average velocity of the bus during each of the segments and over the whole trip. Okay, let's see if you guys can do that one. The answers are here. You can check if you did it right. Okay, I want you guys to see if you can do that. Do I need to make that a little bigger? Oh, I can't. I flipped it out somewhere. Actually, you know what? Let's do it this way. I have that in your digital notebook. Come on. Okay. Let's have you guys start with number 5 here. So that's the one we were just looking at. Okay, so you've got that in your online one. If you want to be able to blow that up a little bigger than I can blow it up on here. Okay, that's in your kinematics worksheet book. Okay, it's on the bottom of page 4. I want you guys to try question number 5 there. Okay, we ready to go over number 5? How many people just need a couple more minutes? Okay, give it a couple minutes. Oh, I forgot to pause the recording. So there'll be a big long blank spot in the middle of this. Just like scrub through it if you're watching this a second time. Okay, that happens sometimes. All right, so we got to look at what's the average velocity during all of these parts as well as over the whole trip. It's the same formula regardless of what part or whether we're doing the whole trip. Okay, average velocity is the total displacement divided by the total time. Okay, for part A, that's going to mean that I go from 0 to 25. Okay, so my displacement is going to be 25 kilometers, and that's going to take 1 hour. Okay, so my average velocity then is 25 kilometers per hour in a positive direction because it's velocity and I have to give a direction. Okay, for part B, I go from a position of positive 25 to a position of positive 33. Okay, is what I'm reading that to be. Okay, so yeah, 33. Okay, so that's going to mean a change of 8. Okay, so we have a change in position of 8 kilometers, and that takes from 1 hour to about 2.2 hours, 2.25 hours. Okay, so that's 1.25 hours. Okay, so if we do that, we should get 6.4 kilometers per hour, and that would also be positive. Okay, everybody all right with that? It's kind of tough to see the lines on that graph. Right? And then over the last bit, I go from a position of 33 kilometers to a position of 27 kilometers. Right? So for that last part, my change is negative 6 kilometers now, okay, because I went from positive 33 to positive 27. Okay? And that takes from 2.25 to 3.5 hours, so it's another hour and a quarter. Okay, so that should give us negative 4.8 kilometers per hour. Okay. Questions on that one? Right, now we have to do over the whole trip, right? Because that's the one thing we haven't done yet. So total displacement over the whole trip is 27 kilometers, positive 27 kilometers, because I start here and I end here at positive 27, right? So over the whole trip, we're going to have positive 27 kilometers. That takes 3.5 hours. Okay, and so when we divide that, we should get positive 7.7 kilometers per hour. All right. Okay. Is this position versus time graph stuff ringing a bell? At least a little bit. so let's look then at velocity versus time graphs. Okay, so a velocity versus time graph, similar, except instead of showing where the object is at various points in time, it tells us or shows us how fast the object is going at various points in time and in what direction. Right? So on a position versus time graph, if something was traveling at a constant velocity, then we had a diagonal line. What does a constant velocity look like on a velocity versus time graph? A horizontal line, right? Because the velocity is not changing. It's easy to get confused when you're looking at the graphs. Okay, that's why it's always important to look at what the axes on the graph are first and then look at the lines. Okay, know what's on the graph before you start thinking about what the graph is saying. Right, because the most common thing I see is people assuming a graph is a certain kind. And on a multiple choice question, I'll have that answer on there, okay, where you've assumed it was something else. I'll put that on there and you'll go, I'm so smart. I see my answers on there. I was right. And you won't be, okay, because you didn't look at the graph carefully enough. Okay, these two graphs, what do they have in common? Yeah. Okay, well this one's position versus time, but this one's velocity versus time. Okay. They're both showing an object moving at a constant velocity. In fact, they're not only showing an object traveling at a constant velocity, they are showing the same object traveling at the same constant velocity. These are graphs of the same movement. One is the velocity versus time, the other is the position versus time. Right? The way we can confirm that is this. This graph, if I calculate the slope of this line, will that tell me the average velocity of the object? Right? Because it's position versus time graph. All right, so if I do that, I'm going to say, I'm going to go m equals y minus b over x. Okay, I'm going to say y is this point right here. That's 1400. Okay, I'm going to use b is 100, so minus 100, and divide that by the total time, 5 seconds. So I got 1300 over 5. That should give me 260 meters per second. Is that right? Okay. Now look at this graph. Okay, it's showing something moving. Here's the 250 mark. That's about 260 meters per second for 5 seconds. They're showing exactly the same thing. All right, so there's no acceleration on here. What's the total displacement of the object on this position versus time graph? Hint, the answer's on the board. I wrote it. Not 14. 1300, right? Final position, 14, minus initial position, 100. The total displacement's 1300 meters. All right, over here, could I calculate the displacement from this graph, from the velocity versus time graph? Okay, I can, and I can use the same formula. Okay, velocity is displacement over time. I just got to take the d, okay, and get it by itself. So I'm going to multiply velocity, which I already know is 260, by the time, 5 seconds. 260 times 5 is going to give me the same number, right? It's going to be 1300. Did I just calculate the area underneath that line? Did I just go height 260 times the base 5 seconds? Okay, you probably learned that in Science 10, right? If you calculate the area underneath the line, it gives you the displacement on a velocity time graph. Okay, the reason for that is it's just manipulating this formula. All right, let's look at this graph in a different shape. Let's say that instead of having a flat line, that it looks like this instead. What's that object doing? It's accelerating. Okay? Its velocity is changing from 100 to 400 over 7.5 seconds. Okay. Can I calculate its acceleration? Okay, maybe we should take out our formula sheets and see if we have a formula for acceleration on our formula sheets. Did you get one? Right, okay. One of the formulas, and there are many on your formula sheet, for calculating acceleration is that acceleration equals the change in velocity divided by the change in time. Okay, you might have seen that in Science 10 like this. Is that strangely like the formula we used on the position time graph to calculate velocity? Final position minus initial position over time. So could this be calculating the slope of that? Okay, this is B. I'm going to use this up here for Y. This is going to be X. Okay, M equals Y minus B over X. Well, Y is the final velocity, 400, minus the initial velocity, 100, okay, divided by time, right, which is, we'll say, because we did it this way, 7.5 seconds. Okay, that's exactly what I would have written if I used that formula. Right? So that formula that you learned last year calculates the slope of a line on a velocity versus time graph. Okay, so acceleration is the slope of a line on a velocity versus time graph. Everyone all right with that? Okay, I want you to calculate the total displacement of this object. So the line that I just drew there. I want you to find the total displacement. Okay, so what's happening in that first part? Yeah, they're accelerating. Okay, their velocity is definitely increasing. Okay, it's getting faster and faster and faster from like just above 0 to around 8 meters per second. And then here, what are they doing? Right, they're moving at 8 meters per second. And then after that, they decrease their velocity. In fact, they actually come to a stop because they come back down to 0, right? That line goes right down to 0. So they actually come to a stop in that last section. This is what a sprinter's graph, if they're running like the 100 meters, right, would look like. There would be the part where they're accelerating, and then there'd be the part where they can't run any faster and they run at their maximum speed, and then they cross the finish line and they come to a stop. This sprinter's not overly fast because they only run at 8 meters per second, okay, which would not get it done, but it's essentially what it would look like. Okay? All sprinters would have the same shape. It would just be how high does their graph go. Okay? If you're talking about Usain Bolt, okay, when he is at his maximum speed, he's slightly more than 16 meters per second. Okay? Imagine that. When Usain Bolt is running as fast as he can, he runs from this wall to the other side of the hallway, plus a little bit, in 1 second. Okay? That was when he's at his peak. I know he's kind of older now and he's retired, but okay, when he was at his peak, that's how far he could go in 1 second. Right? He doesn't run the whole race at that speed, okay? But he has to accelerate first. Okay? But for a lot of the race, that's how fast he's running. Like, don't get in the way. Okay? He'll run you over. All right. So things to remember about velocity versus time graphs. What can you read right off of velocity versus time graph? The velocity of the object and the time it occurs at. Because that's all it shows, velocity and time. Okay? The slope of the line can help you calculate the acceleration. The area under the line can help you calculate the displacement. Okay? Again, I'm not encouraging you here to memorize those things. Okay? That's why I walked through all that stuff on here's why the area does equal this, okay? So that you can do that on other types of graphs. Excuse me, as well. Okay. All right, any questions on velocity versus time graphs? Hopefully most of that is review because you did do both types in Science 10. Okay, So I want you guys to do this question here. It's number 6 on that sheet we were just on, but it's a velocity versus time graph now. All right, and it's of a snowmobile. Okay, so I want you guys to answer that one. Okay, and I also want you to answer we'll do the next one after that. Just concentrate on number 6. This is not part of number 6 here. Okay, so don't get it confused. All right, just try number 6 for right now, and I'll go over it with you in a few minutes. All right, so the first parts of this are fairly straightforward, okay? If for the first one it says what's the average velocity during each segment. So in part A here, this first part, okay, we go from 0 to 40 kilometers per hour. So what's our average? No, 40 is our final. That's the fastest we went. We started at 0, we went to 40. Our average is 20, okay? It has to be. That's halfway up. Okay, that's the thing we were talking about when we calculated the area under the line. Okay, for this part here, the flat part between 20 and 50 seconds, the velocity doesn't change. It stays at 40. So what's the average? 40. Okay, and then for the last part, we go from 40 to 80. Again, uniformly. So if I increase from 40 to 80, my average is halfway in the middle. That's 60. Okay, everyone all right with that idea? All right, now, knowing that, I want you to try and calculate the total displacement.
Why is it kilometers per hour on the graph?
Oh, because I screwed it up when I made it. It was supposed to be. I redid the graph because it was really blurry, and I put the wrong units on. So still the right numbers, but yeah, you're right. According to that graph, it should be meters per second. Right? So what I want you guys to try now, okay, is find, well, actually, no, sorry, try the overall velocity, because you'll have to find the total displacement in order to do that. Okay, so I want you to find the average velocity over the whole trip. That will mean you need the total displacement and the total time, which of course you can read right off the graph. All right, so I'll give you a few minutes to get the average velocity over the whole trip. Okay, so let's have a look at this. So if I want to calculate the total, or sorry, the average velocity over the whole trip, the first thing I need is the total displacement. All right, so we were talking about how that's like area underneath the line kind of thing. So we can kind of look at it in terms of shapes here. This triangle here, okay, would be the average velocity, 20 times the time, 20, okay? That would give me the total displacement during this time, right? Then I travel at 40 kilometers per hour for the next 30 seconds. So I would essentially be going 40 times 30 to get this, okay? Then the person or the object, the snowmobile, accelerates. But this triangle here, okay, is only going to calculate how far the snowmobile goes while it's accelerating. There is also this displacement here that it covers because it was already going 40 kilometers per hour. So I actually have to consider not just the triangle there, but also how far does it go because it started at 40 kilometers per hour and then accelerated from there. All right, does everyone kind of follow me on that? So I have to calculate kind of all of these boxes or all of these shapes. So I'm going to go, for this first triangle here, I'm going to go 20 times 20, which is 400, divided by 2 because it's a triangle. Okay, so this here is going to be 200. Okay, then we're going to have 40 times 30, okay, which would be 1200. And then I'm going to have the height of this triangle, which is 40, okay, because it goes from 40 to 80, okay, and that happens over 10 seconds. So 40 times 10 is 400, divided by 2, okay, is 200, and then I have this box here that's 40 times 10, so 400. Right? Everybody with me on how I calculated those displacements? Okay, I'm still average velocity times time, but I know I did it from a more of a kind of geometric perspective. Okay. All right, so now I can calculate my total displacement. So I've got 1400, 1800, okay, 2000. Sorry, that's not right. Yeah, that's right. Okay, so I've got 2000, well, meters or kilometers, whichever one we decide. I guess we're not going 2000 kilometers on a snowmobile. Okay, all right. Hey, and that took 60 seconds. Right, that's what we've got there. 600. Yeah. Okay, so this answer I don't think is right. But 200 over 60 2,000, sorry, over 60 should be 40. Is that right? No, that's not right. What do we get here, guys? 33? Okay. Meters per second is the way we did it, right? Is the average velocity of the snowmobile, which is really fast. 33 meters per second is 120-ish kilometers per hour. It's a ridiculously fast snowmobile. Ridiculously fast. Okay. All right. So questions on how we did that one? Everybody okay with that? Okay. On your worksheets. Okay. I want you guys to try question number 7 right now. Right? You'll want to just draw a freehand graph. It doesn't have to be to scale, okay? But you'll need a freehand graph to do this one. Okay, so let's have a look at how this one's going to work here. Okay, so we will look at just number 7 here. Get rid of that. Oh, but I cut it off. Anyway, we'll be able to do it. So we have person drives at 25 meters per second for 10 minutes. Now the first thing I want to do if I'm drawing this graph is not use minutes. Right, I've got a velocity in meters per second, and then I've got time in minutes. It's not hard to convert, okay, over. So we're going to start here at positive 25 meters per second. So this can be meters per second, okay, velocity. And that's going to go for 600 seconds, because that's how long 10 minutes is in seconds. So that's the first part of our graph. Then they run out of gas. Now, we're not going to draw that, you'd probably coast to a stop and have this curve in here. We're going to assume that the magic of this is that they instantaneously slow down and get out of the car and start walking all in an instant. That's not really what happened, but that's what we'll say happened. Okay, so they walk at 1.5 meters per second, okay, for the next 600 seconds, right? Or, yeah, for 10 minutes. I know that slants up. It's not supposed to. Okay, for 1,200 seconds.
Sorry for the interruption. During scheduled help for all students who have an OS learning strategies course on their timetable, please come to the computer lab. As if you have an OS in learning strategies on your timetable, please come to the second computer lab. Thank you.
Okay, then they're filling up the gas for the next 5 minutes, which is 300 seconds. Okay, so that's going to be 1,500. And then they walk back to the car, but they walk slower because now they're carrying a full can. So we'll look at that tomorrow. Okay.